Okay. Making sure everything's working. Looks like it. Okay, another impromptu live session. Again, this is not planned like I normally would do. I think it's kind of fun sometimes to just explore and document that, because you kind of see how people work that way, and sometimes you find cool tricks. What I wanted to do this time was develop some tooling for identifying low quality information in my RAG system. If you watched the previous video around creating synthetic data with LLMs for evaluation, you'll see we came across some things that like it took a little bit of digging to find chunks that weren't nonsense. So let me give you an example. Here, maybe I'll duplicate this. We'll call this corpus data curation POC. All right, let me get rid of that. Identify and label low quality information that enables us to get out during retrieval. So maybe we just delete it, but I was thinking at the very least we could assign something like a quality score to the chunk, and then that way we could dynamically adjust our filter for how aggressive we want to eliminate based on that score. Okay, so the plan is, what is the plan? Analyze our chunks. Develop a strategy for identifying chunks with low information quality. For RAG systems. Assign a quality score to each chunk and include it as metadata in our vector DB. This enables quality-based filtering. Okay. So that's the plan. Let me select my kernel here. Okay. It's not picking this up. Little things like that annoy me, because then when I need to dig into the code, it tells me I can't find it. So let's wait for it to resolve this. I know this environment has these packages. Why is it not picking this up? How do I refresh this? Yeah, it picks it up just fine here. Weird. 3.10.12, 3.10.12. Yeah, it's the same environment, clearly. I don't know. Let's proceed. Actually, I'll just reopen it. Oh, interesting. It didn't save the kernel. What is happening here? I don't know. I tried the easy thing. I'll address it if it gives me issues. All right. I'm going to take just a sample of 10 chunks and take a quick look at them. I just want to get a feel for how many I think are garbage, basically. Okay. Deprecated. Otherwise, I would say that's a pretty good chunk. Defining and customizing nodes. That one's maybe a little long, but pretty good. Callbacks. Okay, that's pretty good. All right, I would say this is a questionable chunk. That could be a useful link, but that's borderline. Okay, that one's good. I cannot imagine that's a good chunk without any other context. I mean, I guess there's metadata. But this is the sort of thing I want to filter out. Here's another one. So I guess this is defining the API or something like that. Okay. So it looked like maybe 20% of them were bad based on a very quick look. Let's change our seed and look at 10 more. Okay, good. Mediocre. Option 1, use temporary legacy imports. Okay, that seems reasonable. Good. So if you're not familiar with this data set, we took the Llama index documentation because it's a bunch of markdown files basically, and then split into chunks based on the markdown headings. So now I'm looking for bad chunks. I would say most of these have been pretty good, actually. This is another one that I can't imagine how the model would use this unless it understood the structure. But I don't know how it would know that unless it's better at reasoning than I am. Okay, so these were mostly good. There was a couple that aren't so good. So maybe the rate is somewhere around 10 to 20%. Okay, the first idea I had for identifying is just looking at the number of characters in the text, and then also looking for something like words. I would guess that some of these more garbage chunks have very few characters. So as a first pass, let's just take a look at that. Okay, let me just delete all of this. Okay. All right, matplotlib installed? Hard to believe. Okay. right, so the 25th percentile, let's just go ahead and look at the distribution. Yeah, I'll do the simple thing. What was the max? Wow, 25,000 characters. I think I'd previously seen that some of these are way too big. Let me just go ahead and manually inspect some of these extremes. Let's see. Okay, so these are just headings, right? So if I looked at the top 20 smallest text chunks based on the number of characters, the entire text chunk is just the markdown heading that's empty. I can't imagine retrieving that chunk would be useful for any task. Yeah, so these also have no new lines in them. So that's another way to detect it. The number of characters is small. Number of new lines is 0. And I imagine once we get up to some of these others that have slightly more content, yeah, we're starting to see non-zero number of new lines and a reasonable number of characters. So presumably we could establish some threshold or some threshold that basically labeled these as not having much information content. And then we could get our text embeddings for these chunks and train something like a logistic regression and see what we got. I would imagine the embeddings would be able to understand these patterns of simple headings from Markdown files. Okay, now let's look at the other end. Let's look at the largest. Okay, so the biggest chunk is almost twice the size as the second biggest chunk. It has 800 new line characters in it. Let's just go ahead and print this out and see what it is. Okay, it has a list of vector stores. So how might we split this into smaller chunks? So first of all, this list of items could be one chunk. And then, if I were manually splitting this, I would maybe start it here. Or maybe here. We could also, instead of using a heading, they're using bold print there. Okay, yeah. And then they go through and give examples for each of those. So ideally, we could if I owned this document and I wasn't just ingesting it, I would just make those markdown headings of some level, and then my natural chunking process would take care of it. Because I'm a little worried, like if I wrote code to split this based on this bold, like what consequences might have that elsewhere? Might that have elsewhere? I guess if I only applied it to those that exceeded some reasonable threshold, then I would probably reduce the blast radius of that choice. And I could have some regular expression that looked at, basically that this started the line and then this ended the line, to prevent, for example, it splitting based on some bold text within a sentence. This is like a particular regex pattern of starting with the bold thing, having text, ending with the bold thing, and then a new line. Okay, that's all code, I guess. All right, let's look at the second biggest. This looks like logging. So I'm asking myself, is this the right chunk, or should it be made smaller? And if so, how would I know that systematically? And in this case, they're basically showing examples of using an agent, and they're printing out the response that they got. And that response happens to be long. I'm not sure what I would do with this. I mean, this is basically just a full example. You could split it into overlapping chunks or something, but I don't know that you would pick them back up at retrieval time. You know, if you get something like this as a chunk, like when are you ever going to retrieve that? Yeah, I think I'll have to think more about bigger chunks, and for now just tackle the small ones. Because I think there's lots of strategies you could have here. You know, another might be I just throw it into an LLM and I say, hey, give me a different document that's much shorter than this but captures the essence. And if there are code responses, give partial responses or something like that. Because it's really these outputs that are making it long. So you could imagine constructing a prompt, passing this to an LLM, assuming it didn't blow up your context window, and getting it to reduce this in size. And then we could maybe chunk that. I think that's probably the path I would take. And there's so few of these that are really big. Let me count the number of words. And by that I just mean splitting on space. Oops. Just a handful of words for those. Yeah, we very quickly get down to like 400 words, up from 2,000. So I feel like the amount of work you would need to do, these are basically rare. Whereas on the low side, there seems to be a lot more of these types of chunks. Let's see. Let's see what the median is. So the median number of words is 37. Okay. So it's still... It's like the 75th, close to the 75th percentile. Interesting. Let me just go ahead and look at one down here, see if I think it's reasonable. I mean, it's basically just a sort of long code block example. But I don't feel like that's a crazy document chunk. So I'm okay with that. So I would say my final kind of takeaway here is that I need a pretty systematic solution for small chunks, but for large chunks, I can probably just do some more heavyweight processing, like tossing them into an LLM and asking for it to condense it. Whereas for a small chunk, I just need to get rid of it or have some reliable way to assign a low score, because it's never going to help generation. But some of these are going to help generation if I retrieve them and summarize them correctly. Okay, so now what I thought I would do is mark some of these as junk based on a quick look, and then use those as training labels on the document embeddings given here for like just a logistic regression, and then apply that model to the rest of the corpus and see how good it is at surfacing garbage. And then maybe I also take a random sample I don't know. There's some interesting things we could do here. One could be, I've done this in a slightly different context in a previous video, but you could basically plot the embeddings and get clusters. And you will see, I think, that many of these that are junk are in similar clusters. And there might be more than one cluster, but there'll be similar types of junk. So for example, I would guess that there's a cluster that just has these headings in it. And we should verify that. And if that's true, then we can very quickly just apply labels to that whole cluster. I also think there will be clusters for the types of examples we saw before that are, I don't know, they look like API definitions or something like that. Yeah, things like this. Like chunks that look like that, I imagine would be in the same cluster. And if we start exploring that, labeling a portion of them, then we should be able to very easily train a logistic regression and apply it, and then just get reasonable quality scores for everything. We might just need to hand label, let's say, 2 or 3 points on each cluster. So let's test that. I think that's an interesting way to approach this problem. I'm going to leave this manual work here. I'll probably clean it up at some point. Okay. So I'm going to get some TS and E embeddings. Is it metrics? No. I forget what they call it. Decomposition or something? Manifold. So X raw, I think it's called vector. Yep, looks good. Okay. All right, let's just take a quick look. All right, now I want some clustering. All right, let's do more clusters. All right, so let's go back up. Let's get the indices of these and see what cluster values they have. Okay, very interesting. So if we look at the cluster assigned to the embedding of this text, we see a lot of 12s. There's a 4 and a 1. Here, let's do this. Okay, so 70% of them are in cluster 12, and 13% of them are in cluster 4, and 8% are in cluster 1, and down from there. So let's go ahead and just inspect cluster 12. First, I want to see how big it is. 322. Okay. Where's that handy little code for, yeah. I want to do this. This is for readability. I'm going to oh, hey, look at that. I was just looking for the heading ones, but it's also picking up these other. So interesting. My only hesitation is if this is like a standard definition and I'm just not aware of it, but the LLM would be good. Like if I asked it for API information, if it would be smart enough to retrieve this chunk and then translate this for me. I guess I could test that. But so far, I'm okay with eliminating all of those. So what would be, I'm thinking, how involved I want to get. One idea is like in the Streamlit app or a Streamlit app, you have the embedding plot. You circle the point you're interested in. That brings up a data frame. And then you can manually label you can provide manual labels and save that. The challenge with that is you then have to keep track of everything that you've labeled and everything that you haven't, and make it a good GUI. And that's just like quite a bit of work. So it might be easier to just find some clunky way to apply labels programmatically. I think the important part is that for a cluster, it's unlikely that everything in here is either bad or good. So I'll need to go down to another, because this is like crude clustering, right? I just put in a number 20. Like if we look at the way this has been clustered. First of all, let me make these points bigger. These are, I'm sure, very hard to see. Like if you look at these gray points, right? You have like gray over here, way over here. But obviously, this stuff is going to be very consistent and similar to this stuff, but not as similar as the points inside of this. So like whatever label these get may or may not be the same junk label that gets applied over here. Although in the k-means clustering, because I have 20 clusters, these happen to be grouped together. So these clusters aren't perfect is the point. Same here. Like we're playing a little bit of tricks because the clustering was done in the full embedding space and we're just looking at the two-dimensional projection. It's an interesting experiment, actually. Let's put in the the two-dimensional version here. It's going to look prettier because we're visualizing the 2 dimensions. I wonder what I'll get in this case. Oh yeah, so now these are spread across a bunch of different clusters. Let's take a look. Where'd it go? First of all, I want to see how big it is. Okay, so it's 100. I think the last one was like 300 something. So it's 1/3 the size. Yeah, it was 322. We once again have those items. Here's our headings. But like this is a good chunk. I wouldn't want to mark that as junk. Same with these. So I'm not sure why these are being lumped together. It might be because my embeddings also include metadata. And these are in the same directories or something like that. But with a quick glance, I think the embedding or the clusters using the full embedding space is working better than using the two-dimensional projection, even though this looks prettier. So I'm going to go back and do clustering in the raw embedding space. I wonder where these are at, actually. Okay, so if I want... So df... Was it 12? 12. Okay. Index.values. Okay, so now if I do... So I'm trying to find the center of this cluster. $23.3.9. Let me make sure I'm aggregating this right. 27. Oh, wow. So quite a bit of variation here. But the center is 23.4. So that puts it... Okay, it's this big spread apart pink one. That's why. I do want to look at the metadata associated with these, particularly, yeah, these top, I don't know, these top handful. Yeah, so it's in the API reference. I'm going to take a look at one of these. I just don't understand this documentation, I guess. Llama Index provides thorough documentation of modules and integrations used in the framework. Use the navigation or search to find the classes you are interested in. Dad jokes. Interesting. Okay, so I could easily exclude these by just simply ignoring this folder. So for m in metadata, if API reference in metadata slash file path and do the opposite. Module guides seems to be common, and then oh, that's cool. I can actually click on the okay, so this is basically splitting out these things. Okay, so there's a bunch of those. That seems fine. So here's an interesting experiment. I have a programmatic way of identifying all of the cases that are in this API reference, right? Because I can just check if API reference is in the file path. So I can use that as ground truth. And the hypothesis I want to test is if I take half of these, they're embeddings, and label them as junk, and then apply that to the other half that I didn't label, how good is the model at identifying them? Because the content is actually different, right? Like if you look at two different pieces of API, the literal text is quite different. It has these like options and members and stuff, but the rest of it's different. So I think that's a nice sanity check for the whole idea of manually labeling some and then training a model to predict based on the embeddings. So maybe I just take those in cluster 12, which obviously have similar enough embeddings that they're being mapped into the same cluster. I split that in half. All of those that are labeled, or all of those that have API reference in the file path, I label as 1, and the others 0, and then do a train test split and see how good we are at predicting. Okay, so let me restate that. So see if a logistic regression model can learn to find API reference chunks based on document embeddings. Okay, hopefully that makes sense of what the plan is. Oops. I don't know, what is it? Model selection? Yeah. Cluster equals 12. Okay. Now we need to set the right labels. So for okay, so 74% are this API reference. Okay. I kind of forget how to use the rock curve display. Okay, very good. So very strong AUC. Let's look at some failure cases. Oh, okay. So it's just always predicting true. I need a different threshold. I don't know. So it seems more likely to predict we get a precision recall curve. It's pretty darn good. I'm interested in these cases. Which are the ones that it's pretty highly confident? But is in fact not. So it's the easiest way to find these. So where y test is 0, true label 0, and y test hat is greater than. So these are the false positives. Now, how are these not? Why do these have label equals 0? API reference. Something's not right here. Oh. I'm messing up my indices. Oh, man. I'm getting something mixed up here. Oh, well, they're shuffled. Okay, that's the problem. All right, let me fix that. All right, same results. So now I should be able to map back to the indices. Yes. All right, these should all be. All right, these are the mistakes. So to summarize, we took a bunch of chunks, we clustered their embeddings, we identified by looking at the number of characters some chunks that are likely to be garbage, and we saw that many of those chunks with a small number of characters are in the same cluster. And when we started looking at that cluster, we saw a couple of patterns, one of which we identified was these API references. So we thought, okay, maybe we can train a logistic regression on those embeddings if we manually label some points as being bad and some as being good. And the way we tested that hypothesis is we identified the fact that we could identify these with perfect recall and precision because they're in one directory. So we had a ground truth for identifying anything within here. And then we trained a logistic regression using those labels, split, of course, into train and test, to see if our embeddings are powerful enough to identify these types of chunks given enough labeled examples. And in this case, the metrics of the model were pretty darn strong. You know, average precision, 99%, ROC AUC, 98%. Not perfect. It does make mistakes. Using a somewhat arbitrary threshold, just so I could look at some false positives, we get this handful, which is a little bit disappointing because they don't look much like the things we trained on. You know, they don't look like this. So I don't know if the embeddings are basically picking up on the small number of characters, things like that. But I think it gives us confidence to pursue the strategy of identifying, which is essentially start with something like this. Let me make this smaller. Start with this. Sample from clusters. Provide some ground truth labels. Ideally, a mix of both good and bad. And then train a model and apply it and see what you get. And of course, you'll see some mistakes. You'll want to update those labels, and you just apply that process. And then what you end up building is a data chunk quality classifier. And once you have a data chunk quality classifier that you've bootstrapped in a data-driven way, then for all of your chunks, you can get that score and put it in the metadata of your database, and then you can filter based on data quality. So you might say, for this query, I want you to only consider chunks with very high quality. Or maybe you include the quality score in the ranking algorithm, something like that. So let me check the time. Okay, it's 10 o'clock. Something I would like to do is basically start that process and just try to manually label some. So I want to sample, I don't know. Let's see how many points are in each cluster. Oh, so 12 was actually our biggest cluster. So what if we sampled the maximum of either 10% or 10? So in this case, we would label half, right? We'd label 10 out of 22. But in this case, we would label 20. Okay. Oops. What did I say? 10. What data structure do I want here? I could... Okay. Okay. Apply operated on the grouping columns. This behavior is deprecated. I don't really understand that. I guess it's wondering what columns. Are they talking about in the apply? I don't know. What happens? Okay, so this is not working. Oh, wait. Yeah, it is. Yeah, so 12 had 32, so I should get, or sorry, 322. So 10% of that is 32. And yeah, that's what I get here. Oh, wait, sorry. It's 237 labels. Eee, okay. Let's try that. Okay, so how do I want to do this labeling? So for cluster index and items. No. Okay. So for cluster 0, these are my indices. All right, let's use my handy dandy texturing thing. Where did that go? Yeah. So this is where a Streamlit app might help. Okay, ask a question. Multiple tools. Okay, that looks good to me. I'm going to label that with 1. That's useful. Okay, and actually, let me change this. I want to be very explicit about my index here. Okay. Get rid of that. Index 0. Yes. Keep that one. Index 1. Yes. I'm sorry, okay. I'm going to put 1 equals junk, 0 equals good. Reasonable. So I'm putting those as 0 because I think those chunks are reasonable. Okay, index 2, tracing with graph signal. Yes, that looks good. Index 3. Yep. Informative. 4. Yes. 5. Yes. Okay, so all of those I think are reasonable labels, or reasonable chunks. That was nice and easy. Let's go to cluster 1. Now this doesn't make sense to me. This is cluster 1? Yeah, these are interesting. So this is its own cluster. Okay, so these are all junk. Let's take a look at cluster 2. To make it scrollable. Okay, that looks informative. Yes. 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 Okay. This one, I think, no. So we have 0, 1, 2, okay, all the way to 7. So we have 8. And the second to last one, okay, so we have 0, 1, 2, 3, 4, 5, 6, 7. Let me just make sure I have the right number in here. Oh, no, I don't. There are 12 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A lot of room for error here. Another reason why a Streamlit app would probably be a better way to go. I just don't know how many times I want to do this. Okay, so let's go to cluster 3. Good, 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 good. All right, all of these marking is good. All right, that one's borderline. I'll keep that one. So 0, 1, I'm sorry. 0, 0. This one will be a 1. It's just a heading. All right, how many do we have here? Okay, looks like a lot of tough decisions here. We have 20. If it has a complete sentence after it, I think I'll keep it. So keep, throw away. Keep. I don't like this one because it refers to something that is out of the context, but that seems subtle. I don't know that that sort of nuance would be capturable in these embeddings. And it might do more harm than good by giving a strong label to that. I'm going to leave that one alone. I'm going to make everything else a 0. So I need 20 overall. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I'm not going to go through all 20 clusters right now. That one's definitely good. All right, 4 is bad. So 2, 3, 4, 5. Oh, we have 6 here. 1, 2, 3, 4, 5. Yeah, so index 4 is actually the 5th element. 0, 1, 2, 3, 4, 5. Oh man, this is delicate. Maybe at the end I'll go through and print out all the ones that I say are bad just to sanity check. That should be much quicker. All right. Onward. Good, 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 good. Yeah. So how many? 8? All good. 2, 3, 4, 5, 6, 7, 8. And I hope it's clear why this will be more efficient than just random sampling, right? Because like these are all bad and it's a big cluster. So we'll get a lot further by using the structure of the cluster. Okay. This already looks informative. So yes, yes, all good. This one's very long. Yep, yep. So how many was that? Okay. 5, and they were all good. 1, 2, 3, 4, 5. Well, hey. We're making considerable progress, actually. Good, good. Yeah. Let's see. Good. Good, good, good. Yep. Then I think the final thing I would do after I get these labels is go back to the ones that had just a small number of characters and new lines and just bulk label those as junk. I think the combination of the cluster level labels and that rule-based label will get me a long way. Okay. Good. I'm going to mark this as bad. It's basically saying ignore me. Good. Bad. Okay, good. Bad. Bad, good, bad. And bad again. Because this is our API stuff. So we might need to drill down into that cluster more. because it has kind of this mix, right, of good and bad. 11. Okay, whoops. All right, so we're more than halfway done. Good, good, good. Yeah, that's good. Good. I'll just copy paste. Okay, it looks like a lot, first of all. So 0, 1, 2, 3, 4, 5. Are there any that are good? That one's good. Okay, so we need 32. And the third from the last one is the only one with a 0. Okay. Sometimes you have to do things that aren't scalable. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. $30, $31, $32. All right, only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 30, 31, 32, and we said okay, so that's 32, 31, 30th. We want to make a 0. All right. Hopefully that's the last big one. Good, good. All right. All good. It looks like there's quite a bit of text in this one. Okay. Good. Good. Yep. 3. Okay, 4. Okay, there's 13, and they're all good. So we will do 5, 10, 15, delete 2. So close. Good, good, good. Questionable. But with metadata, I think it'll be useful. Because I don't know what resources are referring to, but... All right. So we have 6 goods. I'm almost certainly going to mess up the count on one of these. But it's okay, we'll fix it. Yep. Oh, this is the super long one. That was 17, right? Oh, that was 16. Okay. I'm going to leave that long one marked as good because we already talked about a different way of identifying it and handling it. Good. Yeah. Oh man, we're so close. Okay, is this the last one? Yep. So that had 6. Okay. So assert says I messed up the very first one. Okay. Let's check that out. Okay, I did indeed. So what did I say? They were all good. Yep, index 5. Okay. All right, the lengths match on everything else between the indices and the number of labels I provided. So that's good. So I just want to add in labels using my rule from above. Okay. So let's see, how far do we want to go? I think down to here. So I'm trying to figure out what threshold do I want to cut this off at. I definitely don't want to do that. So yeah, maybe at 90. Is that what it was, though? Let's see. Yeah. Yeah, okay. So I think I'm going to take the top 91 after I sort by the number of characters and just mark all of those. Okay. Okay, so add labels based on length. So y ground truth index short equals 1. Add labels based on hand labeling. For cluster labels. Okay, why ground truth dot mean? Okay, so 8%. But let's see here. I'm already making a mistake because I only want to include. All right. Ground truth train equals. Okay. Oh man, I'm trying to think about this. I only have labels for a subset, right? So what I really need is the indices. Okay. I'm going to make everything a label of -1 to start out for unlabeled, basically. So ground truth train equals x short dot copy. Extend. I don't know if extend is a method here, but I want to add those indices to my. All right, we'll see what happens. Let's try and run it. Okay. Oh, concatenate. Okay. So how many labels do I have? $258. All right, so I had 167, 258. Great. So let me make this assertion. Now, I also want to make sure none of my labeled points are equal to -1, which is what I defaulted everything to, right? Okay, so assert not any. Great. Okay, so now let me see what my junk rate is. 54%. Okay. Now I can finally train my junk detector. Test hat. Oh. Now I have no way of evaluating, of course. I could have split this. Let me split it. Okay, I'm going to rename this to labeled. Right here. Ground truth index. Okay. Okay. What is this? Rock curve display. All right, ground truth. GT test. YGT hat. All right, let's see what we get. Hey, pretty good. Let's do precision recall. Also good. Okay, last thing. I want to repeat this plot, except for now I want the color to be my junk score. Oh, interesting. So now we see all the junk is over here, which if you recall, this was the cluster that had all the short stuff in it. But a lot of the high quality stuff is on the left side. But also interesting is you see certain clusters have a mix of good and bad. And these are opportunities for us to provide more labels. Here's another case. It's like it's mostly good, there's a couple bad in there. So if we provide more labels, we'll probably here, one last thing. I want to get the false positives and see where they are. I'm sure there's some here. So how did I do that above? Let me pull these two down. Okay. Okay, that looks pretty good. All right, where did I get those? All right, so my false positives, I want ground truth to be 0. And my prediction to be 1. Now this should be the indexing of my, let's see here. Of my full thing, right? Oh no, that's of my test set. So this is at 6, negative 14. This is at, I don't know, 1, negative 35. I don't know, it's hard to visualize. So for these, we'll plot them again. Black. Yeah. Oh, okay. They're pretty spread out. Anyway, that's enough. Quick recap. We wanted to identify chunks that were non-informative so we can perhaps remove them from our RAG system. We started by looking at some basic statistics of our chunks, like the number of characters, identified a sizable number based on just that. The really big ones, we decided we needed a different strategy, probably use an LLM to summarize them or something like that. And then we trained a model to predict if a chunk was informative or not based on our rule around the length and some labels we provided. And our strategy for labeling was that we randomly sampled from each cluster. Where's the clusters? Each cluster, because we found that within a cluster things were mostly similar. And for example, all the stuff we thought was kind of bad, a large part of it was in the same cluster. So we were able to manually label a handful of examples in each of our 20 clusters, train a classifier, and get pretty darn good results based on the holdout. And interestingly, we have this kind of nice separation, and we have a lead on how to improve even further, which is look into these clusters where there's a mix of both garbage and good stuff, and provide more labels and better labels, and bootstrap from there. Okay, that was kind of a long one. Hopefully it was valuable. I will see you next time.